Okay, so welcome back from lunch. My name is Angie Wolfgang. I'm an NSF postdoctoral fellow at Penn State. And I'm going to be talking to you guys about what you do once you have found your planets in your data, or not, right? Okay, so Monday and Tuesday, we spent a lot of time talking about the wide range of statistical methods that we can draw upon to have confidence or to help us find our planets in our data. But our science doesn't stop there, right? We want to do things with those detections or non-detections. I almost purposely said or not here because you can still do this kind of hierarchical modeling with upper limits and non-detections. So in order to get constraints on some of the physically relevant questions that we're interested in asking and the whole reason why we're finding planets. Okay, but before I go into that, I just want to spend one slide about why all of you should care and be interested in astrostats, okay? So this week, you've really seen a richness, just a sampling of the richness of the problems that we can use astrostats to address. And especially the topic of this conference, this workshop, the intersection between stats and exoplanets, this is really a burgeoning field. All right, so I know after hearing everyone talk about all these different kinds of statistical methods, it's very easy to be overwhelmed by everything that we don't know and we don't understand, or me personally, I don't know or I don't understand. Take that and flip it around, right? This is an opportunity. There is a lot still to be done, and especially with the era of big data coming up. This joint intersection between stats and exoplanets really is just starting, and all of you in this room can make a huge contribution to it. So you've already made a start by coming to this workshop. So hopefully you can identify just one thing that you could apply to your own research from this week and start there and just go from there. Also, follow your confusion. So when I first started learning about stats, I was very confused because, as with a lot of us in this room, I had a physics major. Physicists like to think about things in a very deterministic way. And that is very much not what statistics is all about. Statistics is about uncertainty. And it's about helping us draw conclusions from our data. So there's fundamentally a different way of thinking about things that I had to learn in order to have these statistical tools start to make sense to me. So if you're feeling confused right now, that's fine. Follow that confusion. Pursue it more. Look up some of the references you've been getting this week, and I'm going to give you more at the end of this talk. Look at what people have been doing, ask questions, talk to people about it. Follow that confusion, and if you're really interested, like I was like really confused, and I really wanted to find out what is this doing? What is this tool doing? And it's led me to basically being an expert in astrostats. So follow that confusion. It can lead to good things. Okay, another point that I wanted to make about statistics. So statistics is not something that you do after the physics, and it's not something that you do just because you feel like it, or to supplement the physics that's the main point of your paper. No. Statistics enables the physics. Okay? You might hear from some people, if your research tends to be a little bit more astrostats focused, where's the physics in what you do? Okay? So it's taken me a few years to learn how to respond to that. I respond by saying, how do you know how to compare your model to data? How can you make inferences? Statistics is the thing that allows you to make inferences, okay? And so cosmologists are pretty far ahead of exoplanet astronomers in terms of this. The way that they ask questions is very, very well suited to a statistical approach. So they understand this point, that statistics is the thing that enables the physics. And exoplanet astronomy is getting there. Okay, one last kind of point on the sociology of all of this. So as physicists, we come from a culture of spherical cows. And what this means for when we try to apply statistical tools is that many astronomers tend to ignore or just don't understand the assumptions that go into choosing which tools are appropriate for your problem. And so what this has created is a very narrow set of tools that we astrophysicists have learned how to apply to data. Okay, so a big part of this is to really try to understand the assumptions and the appropriateness of what tools you want to apply to your problem. And why is that important? Because without understanding those assumptions, we get ourselves into trouble. Okay, Eric Ford talked a little bit about reproducible science and how it's been somewhat in the news for medical fields and for social sciences lately. We don't want to get ourselves into that same situation. We really need to understand the statistical tools that we use. So we want to limit the number of retracted detections, and we really don't want to have biased results. So pay attention to the assumptions of the statistical tools you're using. Okay, all right, so enough about the sociology. Let's go to a very commonly used plot in exoplanets, okay? So this plot has a lot of information in it. So what we're seeing here is the mass of the planet, the orbital period of the planet that has been discovered, and then also just the mass of the star, one of the stellar parameters for the hosts of these planets. So there's a lot of information here, and you can maybe start to see structure here. But before we get too excited and start over-interpreting this, first thing that we need to think about when we're looking at populations like this is what is missing in this plot. So I'm gonna have this be interactive. So does anyone have a suggestion for what's actually missing in this plot? Okay, yeah. All right, yeah. So error bars is a big one. What else?
Detection sensitivity.
Yeah. All right. Thanks, Courtney. Yeah. So how relatively easy it is to find a planet at a given point in space here. What else is missing? This might be a little harder. Okay, yeah, sure, non-detections, definitely. All right, and so there might be many things going into whether or not we can or cannot detect them. Yeah, I heard another answer. The what?
Different labels for different planets.
Okay, sure. So we don't know which planets are which. That's definitely true. We also don't know which planets are detected by which method, which goes into the detection bias issue. How easy it is for different planets to be detected. Yeah?
Multi-planet systems and being able to disentangle that kind of whole mess.
Okay, sure. Multi-planet systems. We don't have information in this plot about the multiplicity. Okay? All right. Yeah, one more?
If you were plotting Kepler planets, a lot of them don't have planet masses.
Yeah, ding, 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 ding. Okay, yeah, so there's this huge population here. This is the Kepler planets. But what Kepler actually measures is radius. So there is a hidden assumption that went into making this plot that is not being made explicit here about how you map a planet radius to a planet mass. Okay, all of these are good things. You guys actually brainstormed more than I came up with myself. So this detection efficiency issue, that's a big one, okay? And it's so tempting to use this and to start constraining your physical models based on the population that the observed population. But you cannot do it. And if you see any of your colleagues or friends doing this, just tell them to take a deep breath and then explain to them why this is not a good idea, because you can bias yourself if you do not take into account the fact that, for example, it is harder to find lower mass planets. Of course, this depends on the detection method, but for both radial velocities and if we're talking about radii, the transit method, it's harder to detect smaller or less massive planets. It's also harder to detect planets at longer periods. You just need to observe for longer for RV. But it's also probabilistically less likely that you'll see them for the transit method. Also, it's harder to find planets around more massive stars. Okay? All of these things create this clumping and this structure that you see here. So you cannot take this at face value. Okay? Also, how well are the parameters actually known? Measurement uncertainty, that's a big thing. And this is going to be one of the key points of my talk. Right? So one of the power of hierarchical modeling is that it's a very straightforward way of including measurement uncertainty within a Bayesian framework. Okay? And then also, what kind of planets aren't on here? Are non-detections. All right? So either just because it was very difficult with the methods that we have to detect them, or because they are around stars that just weren't in our sample. Okay? So selection effects, or selection bias. This is another key point. Okay, so my point here is that even when you have lots of and if they're heterogeneous planet detections, that does not mean that you have an unbiased sample that is ready to compare to theory. There is work that is needed to be done in order to transform this into something that is useful to compare to your formation theory. Okay, and this is where more of the advanced statistical methods come into play here. So I'm going to just tell you about one today. I'm going to tell you about hierarchical modeling. Okay, so this is a statistically rigorous way to make scientific inferences about a population or a specific object based on many individuals or based on many observations. Okay. So just a note here that frequentist multi-level modeling techniques exist, but we're going to focus on the Bayesian approach today. And part of that is because of the way that the two philosophies regarding statistics are set up. Okay? So from the frequentist perspective, what the uncertainty or the variability that they test is the variability of a sample. So given in a universe where you could have an infinite number of samples, what's the variability from sample to sample? Okay? This is the kind of question that if you ask this question, you would want to use frequentist methods. Okay? If blah is the true value of something, what fraction of many hypothetical data sets would be as or more discrepant from that value as the observed one? Okay? And you see how this is kind of like twisted around a little bit? It's not, as scientists, we don't really ask questions like this. If you were in industry and you were concerned with quality control, for example, this would be a very natural way to ask your question. But in science, in things like astrophysics, we are interested in the uncertainty we have in our inference. Okay, so the question that we ask is, what's the probability that blah is a true value given the current data set? All right? As an astrophysicist, that feels like a very natural question to me. And that is what the Bayesian framework allows you to say. Jessie made this point in her talk on Monday, that this is how you phrase a p-value. But this is the way that we like to misinterpret p-values. So just don't use p-values. Go the Bayesian way. And then you can actually say what the probability that your parameter blah has a certain value. Okay? So another graphical way, I think in graphs. So a graphical way of going about this is, so the frequentist perspective, you're concerned about many, 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 many samples. So in the limit that you have an infinite number of samples, how are those samples distributed? Okay? Whereas in the Bayesian approach, you really only have one data set, and you're trying to make inferences on that one data set. So what you do instead is, instead of thinking about many, many samples, you think about the range of allowed values for the parameter. And so that's what the probability distribution means in the Bayesian framework. So there's I've heard a couple people say this week that MCMC is just like maximum likelihood, except you have a prior. That's wrong. There's a philosophical difference in the way that these problems are approached. Okay? You're actually answering different questions. when you do MCMC versus MLE. Okay, so it's been a couple days since we actually heard about some of the methods from Bayes, so I'm just going to remind us what Bayes' theorem is here. So there's nothing really particularly special about Bayes' theorem. It just comes straight out of conditional probability. So I've written in this in the proportionality way. So if this is an equal sign, then we would have a divided by a big integral that is the Bayesian evidence. But I'm ignoring that right now. Okay, so we have the posterior, the likelihood, and the prior. All right, you've heard these over and over again. What do those actually mean, right? Okay, so we heard from David Kipping on Tuesday how to evaluate this, how to actually get some samples from this using MCMC. And you want those samples so you can infer the value of this theta from your data X. But let's just get a closer look at what this means, because I'm going to be drawing from it in a second to go hierarchical. Okay, X is the data, theta, this is the parameters of the model that you want to test. And then when I have this P parentheses, that means the probability density distribution of. Okay, and then this bar means conditional on. Okay, so the prior probability, another way to think about that is how probable are the possible values of your parameters in nature. Okay, so given nothing else, what do you how probable do you think things are? Believe it or not, we do this all the time as scientists. All right, it's better to make these priors explicit. Okay, so this is the likelihood here. So what this does is it ties your model to the data probabilistically. Okay, so the question that you should have in mind when you see a likelihood: how likely is the data X that you observed given the specific parameter values that you have? Okay, so again, this is a probabilistic statement that you're making. And then a posterior probability here. So this was mentioned a couple times. You can see it as a new prior distribution that's updated with information contained in the data. So the question is, what is the probability of different theta values given the data and your model? Okay, your model is a key point in this, and Ben talked about that when he talked about model comparison. Okay, so just giving an example. Okay, so I find that things often get more clear when there's a concrete example in front of me. So I'm going to do that for you guys here. Okay, so our example here is getting orbital parameters from radial velocity data. Okay, so here we have the radial velocity as a function of time. This comes from Kat Fang's paper using RunDMC, which is a differential evolution MCMC algorithm that Ben actually developed. He didn't talk about it, but it's pretty awesome. You should check it out if you do radial velocity stuff. Okay, and these are the data. So our X is the just over 100 radial velocity measurements that we have. Our model is a two-body Keplerian orbit. And then the parameters are things like the orbital period, this is for each planet, orbital period, the time of pericenter, eccentricity, argument of periastron, the semi-amplitude, and also stellar jitter. All of these things can be summarized as this function that maps those parameters to the data, right? And so that's what this line is here, okay? But I'm putting specific emphasis on this because this function is not your likelihood, because it deterministically ties your parameter values to the data, okay? You need some way of incorporating this into a probability distribution, okay? The way that statisticians like to do this is by allowing there to be variability as noise, okay? So specifically, if you are used to using chi-squared for fitting, then you are the likelihood that you're implicitly assuming is this, okay? So here's your likelihood. This right here, that mean value, oh, of course, this is the Gaussian distribution. So where your model actually, your deterministic model fits in is right here, okay? That's the mean value, and what this describes is how the randomness is distributed around your model, okay? How the error is distributed. And so this can describe your statistical measurement error, for example. Okay, another way of when someone says that you're assuming Gaussian noise, this is the equation that they're using or assuming. Okay, another way of saying this, if you could redo a specific data point many, many times, then you would see that they are distributed kind of like a Gaussian, okay? All right. So that was a 1D example. 2D, because this can be confusing, distinguishing between the model and what your likelihood actually is. So, for example, a lot of the time astronomers find themselves fitting PSFs to images. Okay, so this is an example of it. So you have your raw data, you have your function that you're trying to fit there, and that function has some parameters here. And you can see this actually with the likelihood now in the third dimension. So your data here is this matrix of pixel brightnesses. This is a 2D example here. Your parameters are the location and then the width of this model, of the Gaussian PSF. And so your model here is this two-dimensional Gaussian. But also, your likelihood can also be Gaussian. So I bring this up just to really bring home the point that things can be confusing if both your likelihood and your model are Gaussian. So here, the 2D Gaussian describing the point spread function of your star just lives here, and then this is the noise covariance matrix. So you're actually allowing there to be correlations, spatial correlations in the data. Okay. So now that I made that point, we're going to go back to this, okay? And so we just talked about just one way to write down a likelihood using when you are assuming a Gaussian noise, which is implicitly what you're assuming when you do chi-squared. Okay, what about the prior? Okay, well, we heard a whole talk about this from David Kipping on Tuesday. So I'm just going to summarize some of the options here, okay? So if we have a previous measurement about what that object's metallicity, redshift, etc. Well, for planets, it would be a previous measurement of, for example, the orbital period or the eccentricity, even the stellar jitter. Okay, then we could use that previous measurement with its error bars as this prior. Okay, so that would be an informative prior. And honestly, if we have previous information, then we kind of want to use it. So it's a good option. Okay, I'm just beating that horse dead. Okay, so also what you could do is you could choose a wide uninformative distribution for the parameters that we don't know very well. Okay, this is not always a uniform distribution. You're really going to want to think about very carefully about what your parameterization is and how much you believe that parameterization, and consider. So there are many ways to calculate this. There's Jeffreys priors, there's reference priors, there's a lot of different options. So Google some of those terms and you'll see. Okay, if your analysis is analytical, then you could use a conjugate prior. But we often don't do that very often in astronomy. Okay, you can also use distributions in nature from previous observations of similar but not the same object. This would be for the same object. Here we're just looking at the population distribution from similar objects. Okay, so we're going to focus here, and this is where we're going to be taking this method to literally the next level, to hierarchical analyses. Okay, so histograms of population properties, when normalized, can be interpreted as probability distributions for those parameters. Okay, so I'm just writing down what this prior could look like given this histogram, and it can be reinterpreted as the probability of these parameters, such as the eccentricity, given these new parameters alpha. I'm going to call these new parameter alpha hyperparameters. Okay. Okay, and this happens when your histogram here is fit with a function. And And you describe that function, so this is the population distribution that you're describing now. You describe that function with the parameters alpha. Okay, so here I'm going to give you another example, just to kind of cement what I'm talking about. So for example, with the radial velocity fit eccentricity. Eccentricity was one of those parameters in our model. Okay, so what we could do is we could go to a prior study about the eccentricity distribution of radial velocity planets and actually use this, this distribution here as the prior on the eccentricity, okay? So again, this is what this would look like for the eccentricity distribution, and this is the distribution that I'm talking about. That is the dotted line here, and from this paper, that distribution looks like this, okay? And as part of this distribution, you have two free parameters that now describes the population distribution, A and B. So they set in this paper A and B to specific values. But you could, in theory, allow those to vary. Okay, and I'm going to come back to this point that we need to be careful of detection bias, selection effects, upper limits, all of that I use to motivate this whole thing. Okay, so in choosing this way to do our prior, we automatically have to care about all of these things that we discussed earlier. Okay, so now that we have a specific example, I'm going to abstract one more time. Okay, so here we have the proportional form of Bayes' theorem. And we take this prior and now express it in terms of this population distribution. Okay, we're almost there. So this is a situation where the population that we already know about helps make an inference about the individual object that we care about. But what if our science question was the opposite? What if we wanted to use the individuals to infer things about the population? And I'm going to say that we are really at the point now in exoplanet science where this is where a lot of our science results are going to lie. Doing these kind of, answering these kind of questions, okay? Right, so another way of saying this, so if this population distribution contains some interesting physics, and getting values instead of assuming values for those hyperparameters, alpha, can help us understand that physics of the population. That's the science question that we care about here. Okay, so now we go from this to this, and this is a fully hierarchical form of Bayes' theorem that kind of forms the foundation for all of this. Okay, so just as before, we have a posterior, we have a prior, and then this altogether is the likelihood. Okay, and I've made here explicit these hyperparameters because they're actually parameters that we allow to vary in our statistical model. We want to get posteriors for them. That's the whole point of asking the science question. But in order to do that within the Bayesian framework, then we also need to have a prior on those hyperparameters. Okay? So it's just extending Bayes' theorem one more level. Okay. Also a note, if you really, okay, oh, right. So I made this explicit that we have both the hyperparameters and the parameters of the individual objects here. We get the joint posterior for them. So what this is telling you is that we can simultaneously get posteriors on the population and on the individual planets. Okay, so sometimes you care about that. Sometimes you just don't care about what's going on with the individual planets. In which case, you can marginalize over theta and then get this fully marginalized distribution here. And this is exactly what the original form of Bayes' theorem was, right? You've just marginalized over that intermediate level. Okay. By the way, this is a process, in case you didn't know, because I didn't know when I first started hearing about likelihoods and stuff. Marginalization just means that you take the integral over the parameter that you're marginalizing over. So it's like flattening. You're flattening the posterior over several dimensions. Okay, graphically. All right, so a very common way that you'll see hierarchical models described going forward is through these directed acyclic graphs, graphical models. So for just a regular, quote unquote, regular Bayes setup, you have your parameters, and you have your observables here. What this arrow means is that the parameters are probabilistically related to the observables, okay? So this isn't your model, that's the likelihood, that distinction that I made earlier. Okay, for hierarchical Bayes, now this is what you have. Okay, so you have the population parameters, aka the hyperparameters here. Those are related to the parameters of each individual object. So each individual object is drawn from that distribution. Okay, and then that is related to the observable. So you can immediately see why this is called hierarchical modeling, because all of a sudden you're introducing more levels into your statistical model. Okay. One more way to denote this. So we have things written out in terms of Bayes' theorem. We have things written out in terms of the graphical model. There's one more way in order to write down hierarchical models, and that's with a tilde notation. And you will see this in papers, like in my own papers, but also in the other papers that I'm referencing you to at the end. So just so you know what this means. This is the model right here. So we have our data that's drawn from the likelihood, and then we have our parameters drawn from the prior distribution. In the hierarchical framework, we have this extra level where we also have, so we have the individual parameters drawn from the population distribution, and then also a prior on the hyperparameters. Okay. So what this, I didn't explicitly, right, okay, so this is a shortcut for the way to draw a graphical model. What this actually means is this plate means that this is just repeated over and over and over again for each individual. So the full model looks like this. Okay, and so what this actually represents mathematically is conditional independence between each individual. So if you have a set of like 20 planets, if you have a model like this, what you're assuming is that the parameters of each individual planet is independent of the other ones, conditionally independent of the other ones. Okay, so the point here is that when you're going hierarchical, the physics that you care about is in the population, whereas when you're just applying a one-level model, the physics that you care about here is in the individual parameters. But that said, hierarchical modeling is not just for populations. It's also if you have many, many measurements that you want to group together in order to make an inference on the individual. So here, let me give you an example here. So, right, so many times in astronomy and in exoplanets, we have the situation where the parameter that we're interested in, even for an individual object, is separated from the observable by a couple different steps. Okay, so for example, if you're measuring the mass of the planet here, that would be the parameter of interest. But your actual data are the spectra. And there's this intermediate level of the radial velocities. Okay, and so the radial velocities are actually your latent variables in your hierarchical model. I haven't seen anyone actually do this. You apply a hierarchical model to get masses from spectra. I will be very excited. Actually, if anyone in this room does this and the first person to do this, I'll buy you a beer, because I think that would be awesome. Okay, so just to make the point that hierarchical modeling is not just for populations. It comes up very naturally for populations. But if your data analysis kind of has these intermediate steps, you can still apply this to that too. Okay, so here again, what's more, let's go to an actual example. So my first foray into hierarchical modeling was several years ago now, looking at the composition distribution of super-Earth planets. Okay, and by the way, if this is interesting to you and something isn't quite making sense, and you want to read more about it, I essentially wrote down my process of learning about this method in this paper. So you can go check it out and read my process of trying to understand what's going on. Okay, so the science goal here, we wanted to understand both the compositions of individual super-Earths. So when I say composition here for this particular problem, I'm talking about the fraction of the planet's mass that exists in a gaseous envelope. Okay? So what we're assuming is a hydrogen helium envelope around a Earth-like rocky core. That's the assumption that we're making here. We're interested in that for individual planets, but also what this distribution is across the entire population. Okay? And that distribution is described by, we chose a parameterized form for this. So that distribution is described by the log normal with mean mu and standard deviation sigma. Okay, this is what our graphical model looked like. Okay, so this is a real life example of what I just showed you. Now, part of the trickiness with these hierarchical models is that you want to make them realistic because you do want to capture things like detection biases and measurement uncertainty. But it's also very easy to kind of go overboard and go as complicated as possible. So there's definitely, you know, some balance that you have to strike there. Right, so this is the individual composition. This envelope fraction that I just defined right there. And these are the parameters of the distribution describing that all of these individual planets were drawn from. This is the transit depth, okay? So we went all the way down to the transit depth so that we could include the uncertainty in the stellar parameters. Okay, that was a big point of doing this. That for the Kepler data, this is non-trivial. A lot of them only have photometric stellar parameters, so you can get uncertainties up to 100%. So heads up, if you're still using the Kepler data, that you need to account for uncertainty in the stellar parameters. Okay, and then these are all other, so this is the incident flux. That's another parameter that we used in order to describe the photoevaporation threshold. This is the core mass of the planet. Of course, we don't know that, right? We don't have a constraint for this. But the beauty of this is that rather than assuming something, we can actually incorporate our lack of knowledge about it, and then our posteriors will have that, will naturally incorporate what we don't know. Okay, so we actually get more honest posteriors by including these things that are important but we don't know. Okay, and this top level described the population-wide distributions involved. This is where the internal structure model, so you need an internal structure model in order to go from a composition to a radius. This is also reiterates the point that I made earlier. Stats is not something that you do after the physics, it's something that enables the physics. Okay? We actually have our models within the statistical model. Okay, and then down here, the last level is the likelihood. That ties your model straight to the data. Okay? If you wrote down Bayes' theorem, this is what it would look like. This is a very interesting exercise that I did for myself. So I kind of impressed myself by how crazy this looks. But I mean, this is just the mathematical summary of what this graph does. Okay, and if you want to see the tilde notation, check out the paper. Okay, results. Okay, so what we were interested in were the parameters describing this distribution, this composition distribution. So this gives us the mean and the standard deviation of that composition. So this gives us the mean, the average percent of a super-Earth's mass that is in a hydrogen helium envelope. That's what this number means. And this gives the dispersion in that number. Okay, so that, oh, by the way, I didn't actually explain what this is. So this is the output of the hierarchical MCMC that I did. Okay, so each point here is an accepted point in parameter space that is consistent with the data. And this is the 68 and 95% credible regions. And this is the mode of the posterior. Okay, so I mean, this is all fine and great, right? And definitely need to actually display your posteriors in your paper, but it's kind of hard to visualize what actually that distribution looks like. So that's what we did over here. So this is the marginal, posterior predictive marginal composition distribution here. So this is actually that distribution that we got from the data. So it peaks right around 1%. So that was that, and also getting the width of this distribution. The peak here had kind of already been guessed at by looking at a smaller subset of planets, but no one had actually characterized the width of that distribution before. And that width is also important because it gives important constraints for planet formation theory. So both of those numbers are important. So that's the kind of thing that hierarchical modeling can do for you. Okay, but not only do you get results on the population distribution, part of the point of this was that you can also get simultaneous results on the individual planets. Okay, so this is what we're seeing here. So this is the radius of the posterior radius of the planet, and also this composition parameter. So this tells us we can read off an individual planet here, and actually see what the range, the allowed range of its composition is, given the specifics for that planet, okay? Oops. Okay, one more note about shrinkage before I wrap up. Okay, so kind of a key feature of hierarchical models is that they pool and share the information of the individual, about the individual objects. They share information in order to get those constraints on the population, okay? So anyone who wants to do hierarchical models has to know what the result of this is, okay? So again, here we have our graphical model. What happens is that information about a specific planet gets kind of pooled with the rest of it. There's information sharing. This is what this represents. It gets pooled around the whole population in order to get an inference on that population-wide parameter. Okay, so what does that mean for an individual planet? So here, so for example, if you could totally just analyze these individual objects by themselves. You could do that. If you did that though, right, this is an example of the kind of uncertainty that you would get in this parameter. So for example, in the example I just showed you, this is the composition parameter, okay? You would get this kind of uncertainty. But when you pool the information among all the individuals, all of the planets, then you can get a much tighter uncertainty. And this, for example, in our situation is the mean of that distribution. So the point here is that just because of the way that hierarchical models are structured, they share information, the fact that they share information in order to get constraints, they are able to shrink the individual estimates, lowering the overall root mean squared error. Okay, so this is a key feature of any multi-level modeling. It was actually one of the reasons why statisticians started to pursue it when it first was being developed, is because of this feature. But the thing that you have to realize is that there's a classic trade-off in statistics between variance, so how wide this kind of thing is, and something that statisticians calls bias, which is different than how we use the term bias. And basically what that means, the bias is just how much offset there is, okay? It's a classic trade-off. And so what hierarchical models do is they leverage this trade-off. And you will see this in the posterior. So an example of this, I also used hierarchical modeling in order to derive a mass-radius relationship for super-Earths. And you can see this property of shrinkage in action, where this blue region represents this probabilistic mass-radius relationship, and then the red represents the posteriors on the individual objects. And I'll just note that this one up here is Kepler 10, Kepler 10c. It had a very, very high measurement, and additional measurements since then has seemed to indicate that the real mass is actually lower. So I'm just pointing out that there is real power in analyzing planets as a population. Okay, so practical considerations in doing hierarchical modeling. So first of all, you really have to pay attention to the structure of your model. Did you capture all the important dependencies and correlations? Because Because if you didn't, then, and you really expect, for example, two parameters to be strongly correlated with each other, but you allow them to be independent, then you're going to get different behavior in your posterior. So you have to pay attention to that. Also, part of the whole excitement and challenge really of doing this is, did you balance realism with a small number of population level parameters? Okay, this is where our job as the scientists come in. We have to make these judgment calls. Okay, also, so that's about your structure, your model. You also, okay, so I spent all of this time explaining what exactly hierarchical modeling is, how it relates to quote unquote regular Bayesian modeling, but I didn't talk at all about how you would actually evaluate these models, okay? Well, thankfully, you can use many of the exact same techniques that David Kipping talked about on Tuesday. MCMC is still very valid for these. In particular, there are several packages that you can use where you code up your statistical model, and it has an adaptive, well, at least JAGS does. These are two different algorithms. JAGS has the adaptive Metropolis algorithm in order to evaluate this. Stan uses Hamiltonian MCMC with a no U-turn sampler. So this is different inner workings, like what David Kipping talked about. But nevertheless, they allow you to code up this hierarchical model so you can evaluate it. Or you could just write your own. Okay, another key point if you are interested in doing this, spend some time testing the robustness of your model, okay? So what you really want to do is generate hypothetical data sets using your model, and then run the MCMC on those data sets and see if you can recover the truth, okay? Because you really want to understand, as soon as these models start developing extra layers, you really want to understand the behavior of those models so that you can trust the results when you apply it to new data. I mean, this is a big part of where my time goes into doing this. Okay. Also, last point, developing and validating these models takes time, and the model itself is a significant result. So if you want to use someone's hierarchical model or build off of it, you really need to reference it, because that's part of the science that we're doing here, is developing the statistical models. Okay, so in sum, why should you look into hierarchical Bayesian modeling? Okay, after all, astronomers have spent decades correcting survey biases without all of this work. Okay, a key point for why is to incorporate measurement uncertainty, because that automatically adds another layer of uncertainty in your model from regular Bayes, okay? But there's a lot of other reasons, okay? So just the Bayesian framework in general allows us to readily quantify the uncertainty in our parameters and allows us to interpret it in the way that we want to interpret it as scientists. Okay? It actually answers that question of what is the probability of this parameter having this value. It actually does answer that question. Okay? Also, you can obtain simultaneous posteriors on both the individual and population-wide parameters. So what this means is that you get self-constraint on both the population and the individual physics. That seems like a no-brainer to me. It naturally deals with large measurement uncertainties and upper limits. Okay? So I showed you these graphical models, right? This lowest level in the graphical model, that's where you incorporate your measurement uncertainty. And the beauty of this is that you don't have to have all the same error bars, right? In order to incorporate that individual into your population analysis. You can have a wide range of error bars, and this will be able to deal with it. It's very straightforward extension of this framework. Okay. Also, you can account for selection effects within the model. And obviously, that's definitely something that we need to do going forward in these statistical modeling, population modeling. Okay. It enables direct probabilistic relationships between theory and the observations. So remember that I inserted the internal structure models directly into the statistical model. All right, that directly ties that theory to the observations probabilistically. Also, I didn't actually mention this when I showed that graph, but it also allows you to do apples and apples comparisons between different people's theories. Okay? You use the same data, you use the same statistical model, you just insert in a new module for a new person's theory. And it really helps compare different theorists compare with each other about their results. Okay? And then also it's a framework for quantitative model comparison, which we heard a little bit about from Ben earlier. Okay, so further reading, here's some introductory material from pretty general to pretty specific. So this in particular occurs all the time in astronomy. So my mass radius paper drew a lot from the concepts in this paper. Okay, and then some applications specifically to exoplanets. So anything from the eccentricity distribution, spin orbit obliquity, Kepler occurrence rates, rocky gas transition, more eccentricity distribution, mass radius relationship. Okay, so but that said, this is like only a handful. There are a huge number of problems that can be addressed. Okay, so if this is interesting to you, and you think that you really want to start applying hierarchical modeling to your research problems, then you should know about this. Okay, so this is a program that's happening next year at SAMSI, the Statistical and Applied Mathematical Sciences Institute in North Carolina. Okay, and they're having a year-long program where they bring in astronomers and statisticians together. And the whole point here is for us to work together on mutually interesting problems. So this is how we further the field of astrostatistics here. There's lots of working groups. So there's going to be large representation from both exoplanets, but also gravitational waves and cosmology, because these are the kind of like more stats-focused fields in astronomy right now. So in particular, this working group will be very applicable to people here. So here is a rough timeline of what's happening. In particular, me and Eric Ford, we're organizing right now a workshop on particularly hierarchical Bayesian modeling. So basically what you just heard about, but actually applying it to real problems. And just come talk to me if you'd like to participate. Thanks for your attention. Okay, good. Okay, so the question was, am I making the assumption that everything is part of the same population? So for the example that I showed you, yes. But the cool thing about hierarchical modeling is that one of the levels that you can introduce is different populations. So you don't have to assume that at all. And in fact, it would be, one of the things that I'm working on now is not assuming that anymore. And generalizing this to maybe more populations. But again, this comes back to this trade-off, right? Of what do you, like physically, what do you expect, and how complicated can you make it, right? You want to kind of like balance the two of them. So to start off with, we did just assume one population. But it's totally doable in this framework to incorporate more than that. Yeah, so I've been using mode to report, oh, sorry, thank you. So it's often convenient in order to simplify and summarize your posteriors in terms of a few numbers, rather than plotting up all of those posterior samples. So what about the choice for that? So you could choose mode, median, mean, that kind of thing. So I've been using the mode because it just seemed more natural to me to use the point of highest probability, posterior probability. I should note here that the joint posteriors for hierarchical models are highly multidimensional. And so it's not just the mode of a two-dimensional marginal posterior, but of the full joint posterior. The mean, I mean, I think that after hearing some of the discussion earlier this week, I will also start reporting the median. I'm a little bit skeptical of the mean, just because everyone knows that that's a skewed summary statistic. Yeah, okay, so Paula's question was, she pointed out very correctly that in the composition distribution example that I showed you, what I actually did is I kind of sidestepped the problem of incorporating selection effects into the model by choosing a complete subsample. And I could do that just because there are so many Kepler planets. So I could define a stellar group such that all of the planets that were there would have been found. But she made the point, rightly so, that what we actually want to do is to incorporate that selection function into the actual hierarchical model. And I didn't do that with my first stab of doing hierarchical modeling because I felt like I had bit off enough. But it's a very valid point, and that is where we are going with this. And you guys can help contribute to that.
Questions? If not, thank you again, Angie.
Thank you.